In fact, one of the later slides will compare them. Okay, we'll come back and compare them. Let's just summarize the operations. We generate keys or round keys, sub-keys. So we take our original key and apply some operations to generate sub-keys, K1 and K2 in our case, because we have 2 rounds. The operations of P10, P8 and the shift are defined. They're fixed, they are known by everyone, they're public. They're known by a malicious user, so an attacker knows what they are, and they never change. To encrypt, we apply our initial permutation at the start of the operation. We apply some function, and that's got many detailed steps, using sub-key 1, swap the halves, apply the same function, and then swap using K2, and then to finish the inverse initial permutation. And decryption is the same steps. IP, the function, swap the halves, the function, inverse IP. So encryption and decryption are the same code or the same algorithm, just that we use the keys in the opposite order. And of course we have the ciphertext on input and we get the plain text out. It's not the purpose to remember all these operations or the permutations. It's just to demonstrate that all that we're really doing is the simple operations we saw in classical ciphers. We're doing transpositions or permutations, and in the S box we're doing a substitution. So in the function f of k, the dark grey box, there's 2 S boxes in there that define, we take 4 bits in and we get 2 bits out. They were defined here. So a substitution box. So the cipher is a combination of substitutions and transpositions. And you should have tried this and got to the ciphertext. If you've got any troubles with that, then again, the operations are very simple. It's just a matter of being careful with performing those operations, making it clear in your notes so that you don't make some simple mistakes. The answer, I think the entire steps are on the website for that example. So you can check your answer. So in summary, simplified DES, an educational encryption algorithm, it can be expressed as some equation where those operations are defined. For example, to encrypt, we take some plain text, we apply the initial permutation. On the output of that, we apply our function using K1, subkey K1. The output of that, we swap the halves. Then we apply our function, the same function again, but use K2 as an input. And then when we're done, the inverse initial permutation. And then the second equation is the decryption operation. And you see it's the same, exactly the same, except here we use K2 and then K1. Of course, we've only got a 10-bit key. Brute force is easy. We've only got 1,024 possible keys to try. So from that perspective, it's insecure. But the algorithms or the steps themselves are considered good for such a simple, small cipher. And when we come to the real DES, it's the same. Even though the key may not be secure, the algorithm itself is considered secure. For example, if you knew a pair of plaintext and ciphertext, even with simplified DES, try and work out what the key is. Not easy. So now how do we compare that to the real DES, the thing that is used or is being used in practice? Some of the characteristics, simplified DES, we used an 8-bit block. Real DES operates on 64 bits. So we take 64 bits of plain text at a time. And when we split it into halves, we have 32 and 32 bits, the left and the right half. Real DES has a 56-bit key. And I've said before, in fact, it's a 64-bit key, but 8 of those bits are not used in the algorithm. They're just used for a parity check. So effectively, there's 56 bits of this for security purposes. And there are 16 rounds. We had 2 rounds, 2 applications of this function f. Des has 16 rounds. And as a result, we generate 16 round keys, and they're all 48 bits in length. So there's an algorithm that takes our 56-bit key and generates 16 round keys. The initial permutation, because our blocks are 64 bits, is also a 64-bit permutation. Our function f, uppercase F, operates on 32 bits, whereas if you look in simplified des, I think the light grey box, you'll see it operates on 4 bits at a time. And we had 2 S boxes, S0 and S1. There are 8 S boxes because we have more bits coming in. And again, if you write real des as an equation, we see we take the plain text, an initial permutation just at the start, apply some function using K1, swap the halves, apply the same function using K2, swap the halves, and just keep doing that. You do that, apply that function 16 times. So the function with key 15, swap the halves, the function with key 16, and at the end, the inverse initial permutation. And the decryption is the same. So that, or not shown here, the decryption, same equation, except here we'd use K16, 15, 14, K2, K1. We use the keys in the opposite order. We'll just quickly go through and I'll show you some of the des details. We're not going to go through in any detail, but just to give you an illustration that it's the same as in simplified des, but bigger. The encryption algorithm, initial permutation, round 1 with K1, round 2 with K2, round 16 with K16, and then we finish with the inverse IP. And of course, we take a key as an input and we generate those round keys using, for example, permutations and left shifts. We saw a left shift in simplified des to get K1 and K2 and so on. And same in simplified des, the operations, those permutations are defined and fixed. So they're always these values. For example, the initial permutation, the first bit, if you read it row by row, moves to the 40th position here. The second bit on the input moves to the 8th bit here, and so on. And the inverse, we see that the 40th bit moves to the first position, the 8th bit to the second position, and so on. You'll see some pattern there, those permutations. On their own, they don't add any security, but they assist in getting the correct ciphertext out. And again, the permutations, expand and permutate are defined, the different permutation functions are defined. And a single round, our function f of k, we take our halves, expand and permutate the right half, XOR with the key, S box, permutate, XOR with the left half, and we get our output. If you look back and compare to the simplified des, it's the same algorithm, same steps. There are 8 S boxes, not just 2. We have 48 bits in. Each S box takes 6 bits as an input, so 6 lines here, and produces 4 bits as output. So we get 32 bits out. And the S boxes are defined. And similar, you look up the row and the column based upon the input, and it gives you the value of the output, a 4-bit output. It's shown here as a number between 0 and 15, a 4-bit value. And the other operations. That's for the block ciphers, the symmetric ciphers, that's the only one we're going to go through in any detail, and that's all the detail we're going to go through. In some later ciphers, maybe after the midterm, we'll see asymmetric cryptography. We'll go through some details, but they're in fact much simpler than this. There are many other ciphers, block ciphers. They have similar design principles. So let's comment about the issues with design of the real DES and the potential for attacks. One measure of the security of a cipher, and it's related to the measure of how good it is against, or the concept of diffusion and confusion, is called the avalanche effect. An avalanche is when something, say, starts falling, a small stone starts falling at the top of the mountain, and it knocks on other stones, and they knock on more stones, and at the end, many things are falling. So it's a large fall of rocks and so on, snow. So you start with something small, and it contributes to changing many things as it goes. This effect is desirable in ciphers, and it's defined as a small change of the input should produce a large change on the output. That's the idea. So, for example, a small change in the key, if we apply some cipher, we take one key, encrypt with our cipher, we get some ciphertext. If we change that key by just one bit, then what we'd like is that the ciphertext as an output is changed by many bits. Changing just one bit on the input should change many bits on the output. That's desirable. It turns out that DES has this avalanche effect. That is, when you make a small change on the input, it'll make a big change on the output. And from that perspective, it's good in terms of security. DES is considered a strong algorithm. One of the reasons is because it exhibits the avalanche effect. Let's demonstrate with an example. We will not calculate. We'll do two different cases. The first case, we take some plain text input, and it's shown in hexadecimal here. It's a 64-bit block. We take this plain text 1, and we have a key, some key which will use the same value in both operations. We'll encrypt plain text 1 with a key, and we'll get some ciphertext. And then we'll do the same operation. We'll encrypt plain text 2 with the same key, and we'll get some ciphertext. And the difference between plain text 1 and 2 is just 1 bit. Okay, so it's 64 bits. In hexadecimal, we see all of those bits, all those digits are the same except the first digit. So in hexadecimal, if we convert to binary, plain text 1 is, each digit is 4 bits, so 0 here, followed by 2, and followed by all the other bits, whereas plain text 2 is 0, 0, 0, 1, and all the other bits are the same. So there's only one bit that differs in the input, the two different plain texts. So we encrypt P1 with some key, get some ciphertext. We encrypt P2 with the same key and get some ciphertext, and then compare the ciphertext. And this shows that, but it compares the output of not just the final ciphertext, but each round. Remember, in DES there are 16 rounds. So this is the input, our plain text 1 at the top and plain text 2 below it. That's the input to our DES. And at the end, the output is here. This is ciphertext 1, this is ciphertext 2. But in fact, we see the output of each operation, or at least each round in this case. If this is the input to DES, after the first round, the output will be these two values. You can see they're similar, okay? Almost the same. Turns out the only difference the number of bits which are different, if we convert these two hexadecimal values to binary, there's only 1 bit difference. So in the input, there's 1 bit difference, the delta, the difference is 1. And after the first round, there's 1 bit difference. But in DES, we repeat the operation 16 times. After the second round, there are 5 bits different in the output. And after the third round, 18 bits. And then 34, 37, around 30, 32 bits differ. And at the end, 32 bits differ in this example, which is exactly what we want. What we want is if we change 1 bit on the input, then we should randomly change bits on the output ciphertext. And if it's randomly changing bits, half of them we'd expect to change on average. If we've got 64 bits of ciphertext, then a different ciphertext should differ by, on average, 32 bits, half of those bits. So we encrypt P1, we get out the output at the end here, C1, some value, and also if we encrypt P2 with the same key, we get C2. We want, so if we have some bits here, whatever they are, then if we'd like C1 and C2 to be different on average, then half of those bits should be different values. And that's what this counts here. The 32 bits were different, which is exactly half in this case. On average, we'd like half. Sometimes it will not give us exactly 32. Changing 1 bit on input produces many bits changing on output. It doesn't show us which bits, but it just counts the number of bits. We could determine by converting this to binary if you wanted. So in fact, the goal is to produce half of the bits to be different, which we achieve. In fact, after about round 4, we achieve that. So we could have, from that perspective, stopped at round 4. After we do round 4, from the perspective of the avalanche effect, we've achieved what we're looking for. We've changed half of the bits. But we keep going. It doesn't hurt in terms of security. It does hurt in terms of performance. The more rounds you do, the longer it takes to encrypt something. If we stopped after 1 round, this cipher would not exhibit the avalanche effect, because we'd have 1 bit change on the input. If we perform just 1 round, then the two ciphertext values, C1 and C2, would be different by 1 bit. And then an attacker can potentially use that information to take the ciphertext pairs and work out what the plaintext was. If we stopped after round 2, then 5 bits different. Again, they are similar. C1 and C2 would be similar. 18 bits, after 4 rounds, then we start to get significant differences. So that's an illustration of the avalanche effect. Small change on input, large change on output. This is the case where we change 1 bit in the input plaintext, where we keep the key fixed, the same value. We can do the same by keeping the same plaintext, but changing the key value. Take one plaintext value, encrypt it using key 1, and then take the same plaintext and encrypt it using key 2, where key 2 differs from key 1 by just 1 bit. 1 bit change on input, and in this example it produces 30 bits change on output, around our half, around 32 or close to 32. So same plaintext here, but 2 different keys. After 1 round, we got 3 bits different, 11, 25, and now we're around or close to our desirable goal of 32 bits different. So if a cipher exhibits the avalanche effect, then we consider it's good in terms of security. If it doesn't, then that's a potential flaw that an attacker can take advantage of. And DES does exhibit the avalanche effect. And it also indicates that using 16 rounds is a good design choice. If the designers chose to use 2 rounds, it would not be a good choice. Why not use 10 rounds? Well, it would be good from the avalanche effect. It would be better in terms of performance. But they need to make some decision somewhere and say, okay, the more we do, the better for security, but worse for performance. And the decision was 16 seemed reasonable in that case. You could do 100 rounds and it would be more secure, but it would take more time to process. The other part of the security of DES is the key size. So it's considered that the algorithm itself is secure, but what about the key length? What about a brute force attack? So from a security perspective, only 56 bits are used for encryption. 8 bits are for parity check. So from the attacker only really needs to guess 56 bits. We only care about those 56 bits. So how long does a brute force attack take with a 56-bit key? So 2 to the power of 56 possible keys, which is that 70 billion or 70 million billion, you can work it out what it is. Many, so 16 zeros. That's the number of possible keys. So what if we attempt to decrypt? We've got a ciphertext. We decrypt with the first possible key, check the plaintext, does it make sense? If not, move on to the next one. Let us try all the keys until we get plaintext that makes sense. On average, we'd have to try half of those keys to get the right plaintext. So, when DES was designed, or after it was released in 1977, people estimated how much it would cost to build a machine, a computer, that would perform a brute force attack. They didn't build it, they estimated. So this is what, 35 years ago. They estimated it cost them about $20 million at that time, which is quite expensive for a computer, to build a computer that would break it in 10 hours. In 1998, so 14 years ago, the Electronic Frontiers Foundation, EFF, they built a machine that broke DES. So they performed a brute force attack. It cost them $250,000 US, and it took them 3 days to get the key. So at that time, DES was considered insecure because, okay, for you and I, this is expensive, but for an organisation that wants to get secret information, or a government organisation, that's cheap to break DES. So a brute force attack was possible at that case. So the EFF just used commodity off-the-shelf computers and put them together and broke it in 3 days. So 56 bits is considered too short against a brute force attack. It's not long enough. We need more bits. So that's the primary problem with DES. The key's too short. The algorithm is considered secure. People don't know of any, well, there are no known flaws in the algorithm that make it easy to break, but the key length is too short. So people took advantage of that. They knew that the algorithm was secure, or they assume the algorithm is secure. They have implementations of the algorithm in software and hardware. So, but the key length is too short. So people developed triple DES, or 3DES, which uses DES but 3 times. And there's 2 different ways. You effectively, instead of have a 56-bit key, you either double the key length, have 2 56-bit keys, or you can even triple the key length. It's called 128-bit, so 2 times 64 bits. But of course, some are used for parity check. So to increase the key length, just apply DES multiple times using a different key each time. We'll show some examples of that and see why triple DES is needed and why double DES using just 2 operations doesn't work. Maybe a bit later, but definitely today. What about other attacks? And we're not going to describe them. I don't know how some of them work in details. But people have tried to do different types of attacks, in theory mainly, against DES. Not doing a brute force, but trying to take advantage of knowledge of the algorithm, the implementation of the algorithm, to try and break the cipher. One type of attack is called a timing attack. The encryption is implemented either in software or hardware, and each operation, the XOR, the permutations, the S-box, takes some time. What a timing attack does is they try to measure how long each operation takes, and from that, because depending upon the input plaintext, the input to each operation, it may take different time. So from the timing of each operation, try and work out what the plaintext or key is. So observing in a very small detail, nanosecond, so on, what your hardware is doing while it's encrypting something with DES. And if you can work out, okay, encrypting this sequence of bits or applying this operation took 5 nanoseconds, but then the next round it took 7 nanoseconds, then that difference in time can potentially be used to work out eventually what the plaintext or the key was. Possible in theory, but not very useful in practice. A, because it's hard to implement, it's hard to get that information. So when I'm encrypting something, to measure what my computer is doing is not easy. And B, because it's quite easy usually to prevent. The way that implementations prevent or stop timing attacks is to add some randomness to the implementation. So when your CPU is doing some processing, to make the timing different, add some random delays in there, which slows down the encryption but prevents a timing attack. So in practice, it's not useful against DES. Another type of attack, differential cryptanalysis, is to look at when you encrypt two different plaintext blocks, similar like the avalanche effect, look how they evolve as you encrypt them after each round. And from the differences, try and then work out, okay, if you know the ciphertext and plaintext, try and work out what the key or the other plaintext was. In theory, again, it turns out if you use such approaches, then there are techniques that can break DES in 2 to the power of 47 encryptions. Our brute force attack takes 2 to the power of 56. So let's say that's the limit. We want to do better than that. Brute force, maximum number of operations is 2 to the 56. So when comparing attacks, we normally don't talk about time. We talk about how many operations, how many encryption or decryption operations. So brute force, we need 2 to the power of 56 different operations in the worst case. Turns out if we can break DES, that is find the key or the plaintext in less operations, then that's better from the attacker's perspective. With differential cryptanalysis, there are techniques that can break it in 2 to the power of 47, all right, compared to 2 to the 55. That's the average. This is the maximum. Let's write the average. Which would take us 256 times less to break the cipher. Because the difference is a factor of 2 to the power of 8. That is, this attack is 2 to the power of 8 times faster than a brute force attack. Because if it takes 2 to the 55 operations here, this takes 2 to the 47 operations, that's 2 to the power of 8, a factor of difference, or 256. So if our brute force attack took a year on some computer, then this would take a day or two. Still not significant, okay? 256 times is okay, but it's not great in some cases. The problem with such an attack is that it takes advantage of and requires chosen plaintext. Remember when we spoke in one of the first lectures, in general, the types of attacks. The more information the attacker has, the easier it is to attack. And we listed, okay, what do we have? We had chosen plaintext, chosen ciphertext, a combination of the two. So depending upon what the attacker could know, it made it easier as they knew more information. In this case, if the attacker can choose plaintext values, get the corresponding ciphertext for each of those plaintext values, then using that information they can try and find the key. And they can find the key in 2 to the 47 operations, so long as they have about 2 to the power of 47 plaintext values, which in practice is impossible. 2 to the power of 47 different plaintext and their corresponding ciphertext, to get those values is impossible. That is, what? 100, it's almost a million billion different plaintext values, okay? 10 to the power of, almost 10 to the power of 50. So, in theory possible, but in practice not very convenient, okay? Because the attacker would need to get all those plaintext values, store them somewhere, and then they perform the attack. Another approach, linear cryptanalysis, is to try to find some linear approximations, some equations that approximate the relationship between the ciphertext and key, or ciphertext and plaintext. And from that try and work out what the key is. And it turns out using that there are known techniques that are closer to, or a little bit better, 2 to the 43 operations. So 16 times better or faster than this. But, actually, sorry, that's wrong. Using 2 to the 43 known plaintext, I think in terms of the effort, it's similar to this one, around 2 to the 47. But for it to work, again, you need a lot of known plaintext. Less than this, but not many, okay? So in theory, attacks are possible. In practice, DES, the algorithm, is considered secure. But the key length is too short. That's the problem. So brute force is possible. Finally, about the design of DES. It was designed, as we said at the start of this topic, designed or standardized by NIST in the US, but designed originally by IBM and the NSA in the US. And the design was done in private. That is, a company and an organization come up with a design. No one else knew how they made the decisions. Why did they choose the S boxes as they were? Why did they choose 16 rounds, not 20 rounds? And therefore there are some questions about the motivation. And some people had doubts as to whether possibly it was designed such that some organisations could break it if they knew about the motivation for the design. But it turns out in most cases it's still considered secure after a lot of analysis. It's been around for 40 years. People have tried to break it, but it's still considered quite secure. Turns out the S boxes work quite well. They provide confusion in the output. People have done analysis to show that if you took the S box of DES and changed it by just a small amount, the output would be much less secure, which suggests that the design is designed in a way that it produces a secure output. So the S boxes were designed to provide confusion in the output, whereas permutations to increase the diffusion in the output. So that's a summary of the design principles of DES. Algorithm is secure, key length is not. We're going to look at the extensions. We'll look briefly about, okay, the algorithm's good, key length is not. So the first approach is you apply the algorithm 2 times and use 2 different keys. That effectively increases the key length, doubles it, but uses the same algorithm, which is an advantage, and leading to triple DES. And then we'll list some other ciphers. But we'll do that after the break, because it takes, to give some example there, it takes a fair bit of time, which I think we'll not try to rush it right now. Let's try and look at another example. We'll come back to that. How long have we got? 20 minutes. Let's start it and then we'll do the example after the break. That may be easier. So since people consider the algorithm for DES to be good, but the key length not to be good, they wanted to design a new cipher that uses the same algorithm but increases the key length. The advantage is that of using the same algorithm is that you know it's good, you don't have to test it much more, and you've already got software and hardware implementation, so you can reuse the software and hardware. So that's an advantage of continuing to use DES. And the approach, quite simply, is encrypt multiple times but with different keys. And we'll go through the cases. Double DES is you encrypt twice. So we'll see it on subsequent slides. Single DES, we take DES, we encrypt. Actually, let's, instead of give the name, let's just say E to encrypt. We take some plain text as input and we get ciphertext as output, and we take a 64-bit key. That's single DES or normal DES. So for double encryption, take our plain text, encrypt that with a 64-bit key, let's say K1, and then take the output of that and encrypt that with a different 64-bit key, K2, and get our ciphertext. That's all. So the same algorithm here, this is DES used, encrypt with a 64-bit key, we get a 64-bit output, then encrypt that 64-bit output again using a different key, and we get our ciphertext. Again, still 64-bit blocks on input and output. That's double DES. From a brute force attack, in single DES, they need to try 64-bit key, 2 to the power of 64, or we know that in fact only 56 bits are relevant, but we often refer to it as a 64-bit key. With double DES, the attacker has to guess both of the key values, because it's no good knowing just one, because if you know K1, you need to then work out, okay, what value of K2 is given to give the ciphertext. So in double DES, the attacker would need to know both key values. K1 is 64 bits, K2 is 64 bits. Effectively, we have 128 bits that the attacker needs to guess. So there are 2 to the power of 128 possible keys, as opposed to 2 to the power of 64 possible keys. So that's the idea of combining the ciphers together. Use the same algorithm, just apply it twice and use a different key each time. Yep.
Isn't it 2 plus 64?
Let's work that out. Let's simplify, and let's say we have a 3-bit key. No, even simpler, 2-bit key instead. Okay? We have a cipher that takes a 2-bit key as an input. So the values, we know there are 4 values. So the attacker has to guess which key it is. So if it takes a 2-bit key, then there are 4 possible, to the power of 2, 4 possible keys. So a brute force attack, in the worst case, we need to try all 4. Apply the same algorithm. We have a 2-bit key here and another 2-bit key here. So what are the possible values? K1 and K2 can be any of those 4 values. How many combinations do we have? We have 16 combinations, you see, because we could have, so we could have 0, 0 and 0, 0, K1 and this value of K2. We could have 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and then, so there's 4 values, then we can have 0, 1, 0, 0, and so on. So effectively we have a 4-bit key in this case. So 2 plus 2, and so the number of keys is 2 to the power of 2 plus 2 in this case, which is our 16. And hence, if we have a 64-bit key, it increases the length up to 128 bits. It doubles the length. But, and the problem with double des, although the key length is doubled, the amount of effort to break it is not doubled. Is not much stronger than the amount of effort needed to break single des. We'd expect, or we'd hope, if we had 2 to the power of 64 for single des, then we'd hope we'd take 2 to the power 128 operations to double des. But it turns out that's not true. There's another attack that we can perform, such on double des, the amount of effort to break it is about the same as single des, about twice as single des. 2 times the effort is about the same. That is, if it takes 1 day to break single des and 2 days to break double des, then they're both considered insecure. 1 day, 2 days, no one cares, that's still insecure. Same as 1 year, 2 years, well, we just buy a double the speed to computer or spend twice the money and we can break it. So the effort needed to break double des is not proportional to 2 to the power of 128. It's about the same as single des. And that's what led to triple des, which increases the strength. We want to explain why double des is not much better than single des. Then we'll finish on triple des. So this is double des, or double encryption. To encrypt, we take our plain text, apply the encryption operation of des with a 64-bit key. This could be confusing. Sometimes I say 64-bit key, sometimes I say 56-bit key for des. Just remember, des takes a 64-bit key as input, but only uses 56 of those bits. So in fact, from a security perspective, the attacker only needs to guess 56 bits. I'll try and use 56 instead of 64 up here. So we take a key as input, we encrypt, we get some value as output, let's say some value x. Then we encrypt that again using the same cipher, but using a different key, K2, and we get our ciphertext. And the decryption is the opposite. Take our ciphertext, apply des, the decryption form of des. Using K2, we get x, where this x should be the same as that x. Because if we encrypt, you look at this top picture and go backwards. Take the ciphertext, decrypt with K2 should give us x. Take x, decrypt with K1 should give us p back. And that's all this shows, the decryption algorithm. So if we encrypt our plain text once with K1, we get x. And similar, if we take our ciphertext and decrypt with K2, we'll get the same value, x. And that's where a flaw in this algorithm comes in. Because what an attacker can do is what's called a meet in the middle attack. Try and find x, and from that work out what the correct key is. So since we have two 56-bit keys giving us a key length of 112 bits, we would hope that would take on average 2 to the power of 111 operations in a brute force attack. But it turns out if we apply the meet in the middle attack, it takes around about 2 to the power of 56 operations. About the same as single des. How does it work? We'll describe the approach here, and then after the break I'll go through an example that illustrates it. What the attacker does is, first they need to know some pairs of plaintext ciphertext. So the attacker must know, here's a plaintext value, P1, and it knows the corresponding ciphertext C1, which was obtained by encrypting with K1 and K2. So let's say in the past, the users have encrypted some plaintext with K1 and K2, obtained some ciphertext, and the attacker, they don't know the key, K1 and K2, but they have found the value of P1 and C1. They know a pair of plaintext ciphertext. And possibly, or they most likely need to know multiple pairs, more than just one. So that's an assumption in this case, that the attacker has somehow found some pairs of plaintext ciphertext. So a known ciphertext, known plaintext attack. They don't have to choose the values, they just need to know any values. And the aim of the attacker is to find K1 and K2. So what they do, attacker knows two plaintext ciphertext pairs in this case, PA, CA, PB, CB. Let's denote them. What the attacker does is takes the first known plaintext, PA, and does a brute force attack using single des. That is, they encrypt with all known values, all possible values of K1 to get multiple values of X. This is our double des operation on the previous slide. What the attacker does is that they take PA, a known plaintext value. They know that PA was encrypted with some key K1 and K2, and it produced CA as an output. So what they do is they take PA and do a brute force attack. They encrypt PA with all possible values of K1. How many possible values of K1? In our case, 2 to the power of 56. 56-bit key. They need to try 2 to the power of 56 possible keys. And as an output of that, so this is just this operation, they'll get 2 to the power of 56 values of X. If we encrypt the same plaintext with all these keys, we'll get these values of X as an output, whatever the values are, X1 up to X2 to the power of 56. And then what they do, so they store those values of x. They may sort them in a table. And then they take CA, the ciphertext value, and they come from the other direction. They take CA and they decrypt CA using possible values of K2, and the value that they get as an output, if it matches one of these values of x, that it indicates that the value of K2 and the corresponding value of K1 is the possible key. It may not be the exact key, but it could be it could be the key. We'll see why there may be multiple shortly. So coming back here, first step, take the known plaintext, encrypt with all possible values of K1, you'll get many values of x. Next step, take the corresponding known ciphertext, decrypt with all possible values of K2, 2 to the power of 56 values. Take CA and K2 and try all the values, 2 to the power of 56, getting confused. And we'll get many values of x. And remember, the value of x when we encrypt P with K1 and then encrypt x with K2 and get the ciphertext, if we decrypt, this value in the middle should be the same if we use the same key. So if one of the values of x from this set matches one of the values of x from this set, then that's an indication that the corresponding K1 and K2 is the correct key. But it may be that there are multiple matches. And if there are multiple matches, you need to do the same step of the set of possible keys, but using a different plaintext pair. So using, for example, PB and CB. So you do a brute force attack on K1, and then similar on K2, 2 to the power of 56 operations, and then it turns out most likely you'll find a pair of one value of K1 and a value of K2 that give us the same x. And if it's the same x, then that means that value of K1 and K2 can possibly be the key. If they're not the same value of x, it means those values of K1 and K2 are definitely not the key. If we have multiple values, we need to check which one's the correct one. Assuming we get one value here of x, let's say x10, and here an x1043, and they are the same. And there are no other values of x in this set that match the values of x in this set. If just these values are the same, then that tells us for sure that K2 1043 and K1, the 10th value, combined is the key. So the key that the normal user used was the 10th value of K1 and the 1043rd value of K2, because they give the same value of x, the value in the middle. If it works, if there's only one match here, then how many operations did we do? How many encrypt or decrypt operations were applied in that case? We did a brute force attack on the first key. How many operations? 2 to the 56 operations here. And then effectively we do, in the worst case, a brute force on K2. How many? So 2 to the power of 56 plus another 2 to the power of 56. How many is that? 2 to the power of 57 operations. Just twice as many as the normal attack. And if we find the key in that case, that's it, we're done. So we don't need 2 to the power of 112 operations. We need 2 to the power of 56 operations, or approximately, which is twice as many as we need with single deaths. With single deaths, on average we need 2 to the power of 55 operations. With double DES to break it, we need approximately 2 to the power of 56 operations, and that's where double DES is not much secure than single DES. Because if single DES takes $10,000 to break, then double DES takes $20,000 to break in the same time. You just double the compute power. So double DES is not considered secure. Let's try and go through an example of that, but after the break. The last 5 minutes, let's look at one example of the brute force attack. This is not seen. Where is it? Come back. Unsuccessful. This is just a few pictures from some different websites and some details about the attack that was performed on DES. We said before that in 1977 they estimated it would take about $20 million to build a computer to break DES by brute force attack, and in 1998 EFF, the Electronic Frontiers Foundation, built a machine that broke DES called Deep Crack. So using usually some commodity hardware, it cost them less than $250,000 US, and in 56 hours it found a key. So given some key, it could find that by just trying them all. It performed about 80 billion, 80 by 10 to the power of 9 keys per second. So that's the speed it could perform, that machine. So it just tries many keys, gets the plaintext until it gets the right one. And people have come up with other hardware to do it. And this is one example of this software from some German universities and some German company. This is, again, still quite, 6 years ago, 2006, but newer. Again, they just used some dedicated hardware to break DES. And some FPGAs. They had these boards of, I think, 12 or 16 FPGAs on a board and multiple boards like this. So they're dedicated hardware circuits to break DES, to try many keys. And each FPGA could do 400 million keys per second, and they had 120 of them. So 120 times that is the number of keys per second. So they got it down to about 9 days. So that's 6 years ago. And it cost them $10,000. So because computers are becoming more powerful, then the cost and the time to break the ciphers goes down. And at about the same time, a Pentium 4 at that stage, so that's the typical computer then, could do about 2 million keys per second, whereas their FPGA 400 million, about 200 times faster than a normal Pentium 4. Given that, here's some approximate numbers. Because approximately, according to Moore's law, the speed of computers doubles every 1.5 years. So if we assume that, so your computer now, in 1.5 years' time, the same cost computer will be 1.5 times faster. In other words, for the same power, or the same compute capabilities, you halve the cost every 1.5 years. If we assume that, then now in 2012, using that old hardware, $600, $625 to break DES. So using the same approach. So anyone can do that. Given that same simple analysis, it's more complex than that, but following that same simple approach, then how much would it cost to break a longer key? That was on a 56-bit key. Then every time you increase the key length by 1 bit, you double the cost because you double the set of keys. From 56 bits to 57 bits, increase of 1 bit, we've got twice as many keys. And therefore, with the same computer, it would take twice, or the same compute capabilities take twice as much cost because we have to build double the strength of computer. So with 64 bits, today about $160,000. This is in US dollars. 70 bits, so increased by 6 bits to just 70 bits, you're at $10 million to break that using the same techniques. What about in, 15 years' time? So let's say you want to encrypt something now and you want it to be secure over the next 15 years so that no one in 5 years' time can use a faster computer and break it, or even in 15 years' time. Then 70 bits in 15 years' time, $10,000. So not so hard for a small company to break that. 100 bits in 15 years' time with this increasing computer strength, $10 trillion. So again, even a large government cannot break a 100-bit key in 15 years' time. So nowadays, 128 bits is considered secure and what's recommended because it's, again, much, much harder to break than just 100 bits. So that gives an approximation of the amount of effort or cost involved in brute force attacks. Increase your key length by 1 bit, you double the effort involved or double the cost involved. So it doesn't take much to make it practically impossible. We'll have a break, and after the break we'll go through an example of how to break double DES. Check your quizzes, ask me questions.